Today we're exploring the GE9X, an ultra-large private jet that features a massive fan and advanced composites for high bypass, and three swing jets, the enables jets with reduced aeration.
When heat is applied to a metal bar, thermal energy causes its molecules to vibrate with increased intensity. This motion spreads along the bar, leading to a phase change where the solid metal begins to glow and soften.
Inside the core of a modern high-bypass turbofan, we aren't just pushing the limits of aviation, we are defying the melting point of physics.
Most jet engines operate at temperatures higher than the melting point of the metal they are made of. It sounds like a paradox, a machine that should, by all laws of thermodynamics, liquefy itself within seconds. This is the GE9X. It is the most expensive, most powerful, and arguably most over-engineered civilian machine ever built. That ballooned it into the billion. This is the GE9X. It is the most expensive, most powerful, and arguably most over-engineered civilian machine ever built. While a standard engine might cost $20 million, but for a billionaire's flying palace, this isn't just about thrust. It's about solving a material science nightmare that makes this engine cost more than the annual GDP of some small nations. Why does a private individual need a $400 million airframe powered by $100 million engines? The answer is mass versus luxury. Real engineering is a game of trade-offs. To make a jet feel like a London penthouse, you add weight. To keep a 300-ton palace in the air for 17 hours straight, flying from New York to Singapore nonstop, you need an engine with a specific fuel consumption so low it seems impossible. You need more heat, more pressure, and more advanced materials than any commercial airline would strictly require for a 6-hour hop.
Think like an engineer. Let's look at this equation for thermal efficiency. Eta equals 1 minus T cold over T hot. This shows how to maximize efficiency.
By the time the air reaches the combustor in this engine, it is already 700 degrees Celsius just from being compressed. Then, we add fire. At these temperatures, conventional titanium and even advanced nickel alloys begin to lose their structural integrity, a phenomenon known as creep. So, how did engineers solve a problem that physics said was a dead end? They stopped using just metal. The Carnot efficiency equation is eta equals 1 minus T cold over T hot. Eta represents the maximum possible efficiency of a heat engine, and T hot is the hot reservoir temperature. To understand the cost, we have to look at the Brayton cycle. To get more work out of a gallon of fuel, you must increase the overall pressure ratio. This increases efficiency and reduces cost. This is Carnot efficiency. The hotter you run the engine, the more efficient it becomes. The GE9X operates at a pressure ratio of 60:1. For context, the engine on a nickel superalloy versus ceramic matrix composite. CMC is 1/3 the weight and can withstand 200 degrees more heat. These are silicon carbide fibers embedded in a ceramic slurry. They can withstand the blistering heat of the core without melting, and they don't require as much cooling air. It was like running a car with the heater on in the summer just to keep the engine from exploding. By using ceramics, the GE9X keeps that air in the flow path, generating thrust instead of wasting it on cooling. It was like running a car with the heater on in the summer just to keep the engine from exploding. By using ceramics, the GE9X keeps that air in the flow path, generating thrust instead of wasting it on cooling. Then there's the fuel nozzles. Formerly 20 separate parts welded together, they are now a single, 3D printed labyrinth of cobalt chrome. This allows for a lean burn that reduces emissions and prevents hotspots that would destroy the engine. This single nozzle is so complex it cannot be manufactured by any other method on Earth. You cannot just fix a 3D printed fuel nozzle or a ceramic blade at a local airport. If a billionaire's engine has a technical hiccup in a remote region, it can cost millions. These engines are tuned like Formula One cars. They are highly sensitive to dust ingestion and environmental factors. For a commercial airline, that 10% is the difference between bankruptcy and profit. For a billionaire, it's just the price of being able to stay in the air longer than anyone else. To put the cost in perspective, a $100 million engine saves about 10% in fuel over the previous generation. Is the $1.6 billion development of these engines worth it? If we look at it through the lens of mass market travel, perhaps not yet. The technology is too expensive for the average narrow-body jet. But engineering history tells us that the billionaire's engine of today is the economy engine of 2040. The GE9X is a monument to our refusal to accept the limits of materials. We have built a machine that lives in a fire hotter than its own skin, all to shave a few percentage points off a physics equation. It is expensive. It is excessive. But it is the only way to turn a 300-ton metal tube into a sustainable, long-range sanctuary above the clouds. Human ingenuity has a funny way of making the impossible expensive first, and then, eventually, inevitable.